A single radio signal once screamed from the cosmos and then vanished forever. We are counting down the 25 times space scientists were completely shocked, moments that left the world's greatest minds utterly speechless. By the end, you will witness the raw moments where our understanding of the universe was torn apart and rewritten. We will journey through the mystery of an interstellar object that defied all explanation, stare into the first image of a black hole's abyss, and confront galaxies made almost entirely of invisible dark matter. What do you think is the most shocking discovery ever made about our cosmos? That single perfect signal arrived in the late summer of 1977. At the Ohio State University's Big Ear Radio Telescope, a routine sky survey was underway, listening for the faint whispers of the cosmos. The data printed out line by line on simple computer paper, a string of letters and numbers representing the strength of any radio noise. Most of it was the usual cosmic static, but one line from a region of space in the constellation Sagittarius was different. Astronomer Jerry Amon was reviewing the printout days later when his eyes locked onto a sequence of characters so extraordinary his pen froze for a second. The signal strength was recorded as 6EQUJ5. In the alphanumeric code the telescope used, the letter E stood for a value 30 times stronger than the background noise of deep space. It was a screaming spike in the silence. In the margin, Amon simply wrote the word that would give this mystery its immortal name, "Wow," with an exclamation point. The signal was everything scientists had hoped to find. It was a narrowband transmission focused on one specific frequency, just like our own radio and television broadcast. Natural cosmic objects almost never emit such a clean, artificial-sounding signal. It came from a fixed point beyond our solar system, rising and falling in intensity over exactly 72 seconds, precisely the duration the Big Ear Telescope's fixed bowl would hear a signal as Earth rotation swept it across the sky. It was, in every technical sense, the perfect candidate for a message, and then it vanished. Decades of follow-up observations using more powerful telescopes aimed at that same spot have heard nothing but empty silence. The wow signal was a one-time cosmic shout, a doorbell that rang once in the dark and left us forever wondering who or what was on the other side. It remains the most tantalizing, frustrating, and utterly shocking maybe in the history of the search for extraterrestrial intelligence, a ghost in the machine of the universe that we have never been able to explain. That profound cosmic silence was a shock born of mystery, a question mark hanging in the void. But sometimes the shock comes not from what we cannot find, but from what we can measure with excruciating precision. A tiny, stubborn deviation that whispers that our most fundamental laws might be wrong. This was the case with the Pioneer anomaly, a ghostly tug on two of humanity's most distant emissaries. Launched in the early 1970s, the Pioneer 10 and Pioneer 11 spacecraft had completed their grand tours of the outer planets and were now coasting into the eternal night beyond our solar system. As scientists tracked their faint radio signals across billions of miles, they noticed something unsettling. Both spacecraft were slowing down ever so slightly more than they should have been. The minuscule deceleration was equivalent to a 10 millionth of the gravity you feel standing on Earth, a force so small it seemed almost trivial. But in the pristine vacuum of deep space, where the equations of Newton and Einstein are supposed to reign supreme, this tiny anomaly was a monumental problem. It was as if an invisible hand was gently pressing on the brakes, a constant sunward tug that defied all known explanations. For decades, this discrepancy haunted physicists. Was it evidence of dark matter clustering in our solar system? A flaw in our understanding of gravity itself? The potential for a revolutionary new physics sent shockwaves through the scientific community. Teams embarked on a forensic-level investigation, digging through decades-old engineering documents, modeling every conceivable force. They checked for the drag of interplanetary dust, for the faint pressure of the solar wind, even for the possibility of a tiny, undetected fuel leak. The answer, when it finally came, was not written in the stars but in the mundane glow of warmth. The breakthrough required a painstaking reconstruction of the spacecraft's own heat. The plutonium power sources on board generated heat, which radiated away from the spacecraft as infrared light. Through brilliant, meticulous analysis, scientists realized this radiation was not perfectly symmetrical. A slightly greater amount of heat was radiating from the back of the spacecraft's dish antenna, facing away from the sun. This anisotropic thermal radiation acted like a tiny, constant photon rocket, providing the exact minuscule push needed to explain the anomalous deceleration. The shock of the Pioneer anomalies resolution was profound. It was not a portal to new physics, but a masterclass in humility and engineering detail. The universe had not broken its rules. We had simply forgotten to account for the gentle warmth of our own creation. The ghost was not in the machine of the cosmos, but in the machine we had built, a stunning reminder that sometimes the greatest mysteries are solved not by looking outward, but by examining our own assumptions with relentless precision. The warmth of the Pioneer spacecraft was a mystery solved within the framework of known physics, a comforting reminder that the universe still obeyed the rules. But just a few years later, astronomers would be shocked by a discovery that did break the rules, or at least every assumption we had about where to look for new worlds. The year was 1992, and radio astronomers Alexander Wolskson and Dale Frail were focused on a distant speck in the constellation Virgo, a millisecond pulsar known as PSRB 1257+12. A pulsar is the incredibly dense, rapidly spinning corpse of a massive star that died in a supernova explosion, an event of such unimaginable violence that it should have sterilized its entire stellar neighborhood, shredding any existing planets into atomic dust. This object was a dead star, spinning hundreds of times per second and blasting its surroundings with deadly beams of radiation. It was the last place in the universe anyone expected to find a family. Wolskson and Frail were not looking for planets. They were using the pulsar as a cosmic clock, studying the impeccable regularity of its radio pulses. But the clock was ever so slightly off. The pulses arrived a fraction of a millisecond early, then a fraction late, in a complex, repeating rhythm. The only possible explanation was that the pulsar was being gently tugged back and forth by the gravity of unseen objects orbiting around it. Their calculations revealed not one, but 3 worlds circling this stellar tomb. The shock was absolute. Here were planets orbiting a remnant of stellar Armageddon, a place science had declared a permanent wasteland. It forced a complete rewrite of the textbooks. If planets could form from the ashes of a supernova, or perhaps even be the shattered remains of worlds that somehow survived the blast, then they could exist absolutely anywhere. This was the first confirmed discovery of planets beyond our solar system, and it came from the most hostile real estate imaginable. That single finding ripped open the floodgates of cosmic possibility. It proved that planet hunting was not a futile dream, and it gave astronomers the courage to look toward normal, sun-like stars. The pulsar planets were the shocking, paradoxical proof that the universe was far more creative and resilient than we ever dared to imagine, setting the stage for a revolution that would soon reveal thousands of alien worlds. The pulsar planets revealed a universe teeming with unexpected survivors, but they still obeyed the familiar rules of gravity. The next shock would come from a force so strange it seemed to rewrite the rules of cosmic destiny itself. By the late 1990s, cosmology had reached a comfortable consensus. The Big Bang had set the universe flying apart, and for billions of years, the mutual gravitational pull of all matter, both seen and unseen, had been acting as a cosmic brake, gradually slowing that expansion. The only real question for astronomers was by how much. 2 independent teams set out to measure this deceleration by using nature's most precise cosmic mile markers, Type 1, a supernova. These are the spectacular explosions of white dwarf stars that reach a very specific critical mass. Because they always explode with nearly identical brightness, scientists can use them as standard candles. By measuring how dim they appear from Earth, astronomers can calculate their exact distance, and by analyzing the redshift of their light, they can determine how fast the universe was expanding when that light was emitted billions of years ago. The teams, one led by Saul Perlmutter and another by Brian Schmidt and Adam Rees, painstakingly collected data from the most distant supernova they could find, peering back more than halfway across cosmic time. They expected to see that the ancient, distant explosions were brighter than predicted, meaning the universe was expanding more slowly in the past, confirming the gradual slowdown. The data told a story that made no sense. The distant supernova were fainter, much fainter, after years of checking and rechecking, accounting for interstellar dust and every possible error. The shocking truth was undeniable. The expansion of the universe was not slowing down, it was speeding up. Some mysterious, repulsive force was stretching the very fabric of space itself apart faster and faster over time. The collective shock reverberated through the scientific world. It was as if you threw a ball into the air, expecting it to eventually fall back down, but instead you watched it shoot upward with ever-increasing velocity, defying gravity itself. This force was given a name that confessed our profound ignorance: dark energy. The discovery completely overturned the fundamental model of cosmic evolution. Calculations revealed that this dark energy isn't just a minor player. It constitutes roughly 68% of the entire mass energy content of the universe. All the stars, galaxies, planets, and even the invisible dark matter we had been searching for, everything we thought was the universe, was just a minority share, floating in a vast, accelerating sea of something we cannot see, touch, or comprehend. It was a humbling, terrifying, and utterly shocking revelation that the ultimate fate of the cosmos is being driven by a phantom we are only beginning to name. Dark energy painted a future of an ever-emptying cosmos, a grand and lonely fate. But one shock would bring the focus crashing back to our own celestial doorstep, transforming a world we thought we knew into something entirely new. For centuries, the moon was the definitive symbol of a barren wasteland. Telescopes revealed a gray, crater-pocked surface, and every rock brought back by the Apollo astronauts was bone dry. The scientific consensus was absolute. Our moon was a completely desiccated rock. Its water boiled away eons ago by the heat of its formation. This belief shaped every plan for future exploration. It meant any long-term presence would require hauling every single drop of water from Earth, an astronomically expensive proposition. Then, in 2009, NASA decided to stage a cosmic collision to shatter that dry dogma. The mission was called L-CROSS, the Lunar Crater Observation and Sensing Satellite. Its target was Cabeus, a deep crater near the moon's south pole whose floor lies in permanent, profound shadow. A place where temperatures hover just a few dozen degrees above absolute zero, colder than the surface of Pluto. The plan was audacious. A spent Centaur rocket stage, weighing as much as a large SUV, was deliberately aimed like a bullet at Cabeus. Following just behind was the L-CROSS shepherding spacecraft, packed with instruments, ready to fly straight through the resulting plume of ejected material, analyzing it in real time before it too impacted the surface. Back on Earth and from orbit, every available telescope was trained on the event. The tension was immense. This was a one-shot experiment with a very public price tag. On October 9th, the Centaur struck. Millions watched the live feed, expecting a brilliant flash of light. The screen showed almost nothing, a faint, fuzzy glow. To the public, it seemed like a dud, a silent, anticlimactic impact. Inside Mission Control, however, the mood was electric. The lack of a visible flash was the first clue. It meant the impactor had hit something soft, something that absorbed the energy rather than reflecting it as bright light. Then the data from the L-Cross probe began streaming in. As it plunged through the kilometers-high plume, its spectrometers detected the unmistakable chemical signature of water vapor. Not just a trace, but a significant amount. The initial analysis suggested the impact had kicked up about 100 kilograms of water, the equivalent of a dozen large buckets, from a crater floor that was supposed to be drier than the driest desert on Earth. The shock was profound. The moon was not dry at all. It was an icy archive. Water, likely delivered over billions of years by comet impacts, had been collecting in these permanent shadows, frozen in place for eons. This single discovery triggered a paradigm shift as dramatic as any in planetary science. Our moon was instantly reclassified from a dead end to a potential gas station for the solar system. That water ice could be mined and split into hydrogen for rocket fuel and oxygen for life support, making sustainable lunar bases and missions to Mars infinitely more feasible. A world we had visited and left for dead had been hiding a precious resource in its coldest, darkest corners, a shocking reminder that sometimes you have to crash into the darkness to bring secrets to light. The discovery of lunar water revealed a hidden, frozen resource right next door, transforming a wasteland into a potential oasis. But the search for the ingredients of life would soon point toward a far more shocking and dynamic world, one painted in the rusty hues of the red planet. Mars has long been the focus of our search for life beyond Earth, a cold, dry desert world we assumed was geologically dead. Then, in 2003, the European Space Agency's Mars Express orbiter made a detection that sent a jolt through the scientific community. Its instruments picked up a faint but unmistakable signature of methane gas in the Martian atmosphere. On Earth, the vast majority of methane is produced by living organisms, from microbes to livestock. The immediate, thrilling question was obvious. Could this be a sign of Martian life? The shock only deepened as more observations rolled in. Earth-based telescopes confirmed the finding, and NASA Curiosity rover, sniffing the air from inside Gale crater, began detecting sporadic, mysterious spikes. The gas would appear, sometimes elevating background levels by a factor of 10, and then vanish again within weeks. This behavior was the real puzzle and the real shock. Mars has no protective ozone layer like Earth. Its thin atmosphere is bathed in harsh ultraviolet radiation from the sun, which acts like a cosmic bleach, breaking methane molecules apart. Any methane released into the air should be completely destroyed in just a few hundred years. The fact that Curiosity was seeing sudden plumes meant the gas was being released recently and constantly from somewhere. Something on Mars was actively producing methane right now. Scientists were left with two equally shocking possibilities, one geological, one biological. The first involves a process called serpentinization, where certain rocks, like olivine, react with water deep underground in the absence of oxygen, producing methane as a byproduct. This would mean Mars is not a dead rock, but a planet with ongoing, hidden hydrothermal activity, a warm, wet subsurface environment potentially habitable for microbes. The second possibility is the one that quickens the pulse. On Earth, simple microbial life called methanogens thrive in places without oxygen, like deep underground or in the guts of animals, and they produce methane as a waste product. The sporadic nature of the plumes could even hint at a seasonal biological cycle. The Martian methane mystery is a perfect storm of tantalizing clues and frustrating ambiguity. It is a signal that screams of active processes, a chemical fingerprint that could be the signature of hidden geology, or just maybe the quiet breath of a microbial biosphere. Every new spike detected by Curiosity is a fresh shock, a reminder that the red planet is not just a museum of ancient history, but a world that might still be whispering its secrets today. The Martian methane plumes are a chemical whisper hinting at a world that might still be alive. But on a far colder and more distant world, scientists were shocked into silence by something that looked profoundly, impossibly artificial. At the top of our solar system, Saturn spins wrapped in bands of pale gold and butterscotch clouds, a vision of serene, fluid beauty. Yet at its north pole, hidden in darkness for decades, lies a structure so geometrically perfect it seems to defy nature itself. It is a hexagon, a six-sided polygon, etched into the atmosphere with the precision of a cosmic drafting tool. This is not a small feature. Each side is longer than the diameter of Earth, making the entire structure wide enough to swallow 4 of our planet placed side by side. It is a permanent, raging storm, a hurricane with 6 razor-straight walls, and it has been spinning in place for at least 40 years, possibly centuries. The Voyager probes first glimpsed its strange silhouette in the 1980s, but the image was grainy and distant, leaving scientists to wonder if it was a trick of the light or a fleeting atmospheric quirk. Decades later, NASA Cassini spacecraft arrived at Saturn and turned its cameras toward the dark northern pole as the long winter there began to thaw. What it revealed was not a fleeting illusion, but a staggering, stable reality. The hexagon was not only real, it was a towering vortex of cloud banks, a colossal weather pattern deeper than Earth's atmosphere, rotating in sync with the planet's own interior rotation. The shock was visceral. Nature creates spirals, spheres, and chaotic swirls. It does not, as a rule, create giant, rotating hexagons. How could a turbulent, chaotic fluid atmosphere organize itself into a shape you'd expect to see in a geometry textbook or a honeycomb? The leading theory points to a laboratory experiment anyone can understand. If you fill a round pan with water, place it on a spinning turntable, and then spin the water at a different speed, you can create stable polygonal shapes in the fluid, including squares, triangles, and hexagons. Scientists believe something similar is happening deep within Saturn. A fast-moving eastward jet stream at the North Pole might be acting like the pan's edge, while the deeper, slower-moving atmosphere creates shear. This shear could generate a standing wave pattern that just happens to manifest as a 6-sided figure, a harmonic resonance frozen in clouds and wind. Yet, while this lab model creates a hexagon, it cannot fully replicate the scale, stability, or the sheer violence of Saturn's version. The precise recipe of wind speeds, atmospheric densities, and planetary rotation that bakes this perfect storm remains a mystery. It is a monument to the laws of physics operating on a scale we can barely comprehend. A shape so clean and artificial looking that it stands as one of the solar system's most shocking and beautiful puzzles, a reminder that nature's artistry can be far stranger than anything we could design. Saturn's geometric storm was a masterpiece of natural physics, a shape carved by wind and rotation. Yet the next shock arrived not from within our solar system, but as a silent bullet fired from the interstellar dark. In October 2017, a University of Hawaii telescope scanning for near-Earth asteroids caught a faint, fast-moving dot. It was already on its way out, having already slingshotted around the Sun. Astronomers calculated its path, and the result was a profound shock. This object, named Oumuamua, a Hawaiian word for scout, was not from here. Its extreme hyperbolic trajectory meant it was not bound by the Sun's gravity at all. It was the first confirmed visitor from another star system, a piece of another world passing through our cosmic neighborhood. The initial discovery was staggering enough, but the closer scientists looked, the stranger Oumuamua became. First was its shape. By measuring how its brightness changed dramatically as it tumbled, astronomers deduced it was highly elongated, perhaps 10 times as long as it was wide. The most likely form was a cigar or a flattened pancake, a shape unlike any asteroid or comet we had ever seen in our own solar system. Then came the real mystery, its motion. As Oumuamua raced away from the Sun, it did not follow a purely gravitational path. It was accelerating just slightly, as if something was giving it an extra push. For comets, this is common, caused by outgassing when sunlight heats frozen ices on the surface, creating a jet of gas that acts like a weak rocket engine. But Oumuamua showed no visible coma, no fuzzy cloud of gas and dust, no tail. Our telescope saw only a bare, rocky-looking speck. The scientific community was electrified and deeply divided. One camp proposed exotic but natural explanations. Perhaps it was a shard of a Pluto-like world from another system, made largely of frozen nitrogen. As it passed close to our Sun, the nitrogen ice would have vaporized from within, creating a gas jet that pushed it without producing a visible dusty tail. Another idea suggested it was a cosmic dust bunny, an ultra-porous, lightweight aggregate of material that could vent gas from deep inside its structure. Yet each natural model struggled to explain all the observed oddities perfectly. The absence of a clear, conventional answer opened the door to more speculative, shocking possibilities. Could Oumuamua be artificial? The most famous proponent of this idea, Harvard astronomer Avi Loeb, suggested its unusual acceleration and shape were consistent with a light sail, a thin, reflective piece of technology designed for interstellar travel, drifting derelict through space. While most scientists strongly favored a natural origin, the very fact that such a hypothesis had to be seriously debated highlighted how profoundly Oumuamua had shaken our understanding. Here was an object that defied every comfortable category. It was not a normal comet nor a normal asteroid. It was an interstellar messenger carrying secrets written in a language of motion and form we are still struggling to translate. Its brief, silent passage was a shocking reminder that the galaxy is likely filled with countless such strange travelers, each one a fragment of a story from a star we will never see, rewriting the rules of what a celestial body can be as it flies through the night. Oumuamua was a fleeting, silent visitor from the void, a puzzle of motion and form. But the next shock would come from a ghost that did not pass by, but had been sitting in plain sight for eons, a phantom galaxy hiding an impossible secret. In 2016, astronomers using a custom-built telescope array called Dragonfly were peering into the Coma Cluster, a dense swarm of galaxies over 300 million light-years away. Their goal was to find the faintest, most diffuse structures in the universe, and they found one. They named it Dragonfly 44. At first glance, it was unremarkable, a faint, fuzzy smudge. But when they measured its size, the first shock hit. Dragonfly 44 was enormous, roughly the same diameter as our own Milky Way galaxy. Yet when they measured its light, the second, deeper shock set in. This galaxy, the size of our home, contained only about 1% of the Milky Way stars. It was a cosmic ghost, a vast, sprawling metropolis of darkness with only a few streetlights turned on. Imagine a city as large as New York, but with only a handful of houses scattered miles apart, their windows dim. That was Dragonfly 44, an ultra-diffuse galaxy. The immediate question was, what was holding this wispy collection of stars together? A structure that, large and sparse, should have been torn apart long ago by the gravitational tides of its violent neighbors in the dense Coma Cluster. The stars should have simply flown away into the intergalactic void. The only possible glue was gravity, and for that much gravity, there had to be an immense amount of mass. A team led by Pieter van Dokkum turned the mighty Keck Observatory toward the faint smudge. They measured the velocities of its few, lonely stars. If the galaxy was lightweight, those stars would be moving slowly, like a gentle swirl. If it was heavy, they would be whizzing around at tremendous speeds, held in orbit by a powerful gravitational anchor. The data came back, and it delivered the ultimate shock. The stars in Dragonfly 44 were moving incredibly fast. When they calculated the mass needed to keep those stars from flying off, the number was staggering. Dragonfly 44 had roughly the same total mass as the Milky Way, but 99.9% of that mass, virtually all of it, was invisible dark matter. This was not just a galaxy with some dark matter. This was a dark matter galaxy that happened to have a sprinkling of stars. The visible part, everything we could see, was less than a rounding error. The discovery tore a hole in our understanding of galaxy formation. How does a halo of dark matter that massive gather so little gas to form so few stars? It was a cosmic failure on a grand scale, a skeleton with almost no flesh. Dragonfly 44 proved that dark matter and the stars we see can exist in wildly different proportions, that the universe is filled with these invisible giants, ghosts holding the shapes of galaxies with a grip of pure shadow. It forced astronomers to ask a haunting new question: are we looking at the universe all wrong, focusing on the tiny specks of light while missing the immense, invisible architecture that truly defines the cosmos? Dragonfly 44 was a galaxy built from shadow, a universe of hidden mass. But the next shock would arrive not as a slow, ghostly presence, but as a sudden, violent scream across the cosmos, lasting just a few thousandths of a second. In 2007, astronomer Duncan Lorimer was sifting through archived data from the Parkes radio telescope in Australia, searching for new pulsars. Buried in observations from 2001, he found something that made no sense. A single, brilliant spike of radio energy, so powerful it saturated the telescope's receiver. It came from deep intergalactic space, not from within our Milky Way. In the span of 5 milliseconds, this pulse discharged more energy than our Sun emits over 80 days. It was a cosmic flashbulb, blinding in its intensity, and then it was gone forever. The discovery, dubbed a fast radio burst, sent a shockwave through astronomy. What natural process could possibly be that powerful, that fast, and that isolated? The leading theories were apocalyptic, involving the final, catastrophic deaths of stars in ways we had never witnessed. Perhaps it was the collision of two ultra-dense neutron stars, or a black hole shredding a white dwarf star, or a hypernova, a supernova on steroids. These were one-time events, stellar suicides that could explain the immense energy and the fact that no burst was ever seen to repeat. The mystery was profound, a universe filled with random, brilliant screams in the dark. Then, in 2016, everything changed. Astronomers monitoring a source catalogued as FRB 121102, located in a dwarf galaxy 3 billion light-years away, witnessed the impossible. It burst again and then again. This was not a one-time cataclysm. This was a source that could fire over and over, like a cosmic lighthouse with an erratic, furious beacon. The shock of the repeating fast radio burst was even greater than the first discovery. It completely ruled out any model involving a single, total destruction. Whatever was making these bursts was surviving them. The focus shifted to objects that could endure such violence, like magnetars, which are neutron stars with the most powerful magnetic fields in the universe. A starquake on a magnetar's crust, a sudden snapping of magnetic field lines, could theoretically unleash a titanic blast of radio waves. But could even a magnetar's fury account for the sheer raw power of the brightest bursts, some of which release in a millisecond the energy our Sun puts out in an entire year? The repeating nature opened other, even more exotic doors. Could it be from a neutron star orbiting through a dense cloud of material from a companion star, feeding sporadic eruptions? Or something entirely new, a celestial object we have not yet imagined? Each new repeating FRB discovered adds another layer of complexity. Some repeat on a predictable schedule, others fire off in chaotic clusters. We are left listening to a universe that crackles with these brief, deafening signals, messages from engines of unimaginable power that turn on and off in the blink of an eye, a mystery that pulses with the shocking rhythm of a cosmic heart we are only beginning to hear. Fast radio bursts are the universe's sudden, deafening screams, but the next shock arrived as a slow, deliberate wink, a star that seemed to be hiding something vast and artificial in plain sight. In 2015, citizen scientists with the Planet Hunters project, sifting through data from NASA Kepler Space Telescope, flagged a star that made no sense. Catalogued as KIC 8462852, it soon became known as Tabby's star after the astronomer Tabitha Boyajian who led its investigation. Kepler's mission was to find planets by detecting the tiny, periodic dips in starlight caused when they transit or pass in front of their host star. These dips are usually symmetrical and less than 1%, a subtle but predictable dimming. Tabby's star did not play by those rules. Its light curve was chaos. It showed massive, irregular dips, some blocking a staggering 22% of the star's light. This was not a planet or even a Jupiter-sized world. To block that much light required an object, or more likely a collection of objects, covering nearly a quarter of the star's face. Even more shocking was the shape of the dips. They were asymmetric with sharp, jagged edges. A planet creates a clean, U-shaped dip as it smoothly blocks light and then moves away. The dips from Tabby's star looked like someone was randomly pulling a ragged curtain across its surface. The data sent a jolt through astronomy. It was a signal unlike anything ever seen, a fingerprint that defied every natural explanation that immediately came to mind. Could it be a swarm of shattered planets or a colossal cloud of dust from a recent planetary collision? Perhaps, but the scale was immense and the star itself was mature, not a young, chaotic system where such events were common. With every conventional model straining to fit, a wild but scientifically serious hypothesis emerged from the silence. What if we were seeing a Dyson swarm? This is a theoretical concept where an advanced civilization builds a vast array of energy-collecting structures like solar panels, orbiting their star to harness its total power output. Such a megastructure would be irregular, blocking light in strange, asymmetric patterns, just like the data showed. For a moment, the shock was not just about anomalous data. It was about the profound possibility that we might have stumbled upon the signature of intelligence operating on a scale that redefines engineering. Astronomers did not dismiss the idea out of hand. They treated it as a hypothesis to be tested, because that is how science works with extraordinary claims. The race was on for more data. Follow-up observations across the electromagnetic spectrum revealed another clue. The star was dimming not just in visible light, but also in infrared. This detail was crucial. A solid megastructure made of metal and silicon would block visible light but would eventually re-radiate that absorbed energy as heat, glowing faintly in the infrared. The fact that Tabby's star dimmed across multiple wavelengths pointed strongly toward something more natural: dust. The leading explanation today involves a vast, uneven cloud of fine circumstellar dust, perhaps from the breakup of a moon or a swarm of comets on a highly elliptical orbit, passing in front of the star in clumps and streams. This dust would be excellent at blocking light, but too cold to glow brightly in the infrared, matching the observations. The shock of Tabby's star was not ultimately about finding aliens. It was a masterclass in how science confronts the truly unknown. It was the shock of data so bizarre it forced brilliant minds to consider the outermost limits of possibility, to publicly entertain a notion straight from science fiction, and then to systematically, meticulously follow the evidence back toward a natural, if still extraordinary, explanation. It stands as a monument to human curiosity, a reminder that sometimes the most thrilling discoveries are the mysteries that make us question everything, even if the answer is stardust and not star builders. Tabby's star forced us to question the very limits of natural explanation, a puzzle written in starlight and dust. But one shock would deliver not a puzzle, but a picture, an answer so visually profound it felt like witnessing a myth become real. The date was April 10, 2019. For days, a quiet anticipation had been building across the global scientific community. The Event Horizon Telescope collaboration had promised an unprecedented announcement, a result from their years of observation. At coordinated press conferences held simultaneously on 6 continents, the curtain was pulled back. There, on screens around the world, was a glowing, fuzzy orange ring, cradling a central region of profound darkness. It was the supermassive black hole at the heart of the galaxy Messier 87, a cosmic monster 55 million light-years away, weighing in at 6.5 billion times the mass of our Sun. And we were looking directly at its shadow. The collective gasp was almost audible. For the first time in human history, we were not inferring a black hole from the frantic dance of stars around an invisible point, or detecting the X-ray scream of matter falling in. We were seeing it, or rather, seeing the absence it carved into the fabric of the universe. The image showed exactly what Einstein's theory of general relativity had predicted for a century, but which had existed only in supercomputer simulations. That fiery ring is not the black hole itself. It is light from the superheated gas swirling at nearly the speed of light in the accretion disk, bent by the black hole's monstrous gravity into a perfect circle. The central darkness is the black hole's event horizon, the point of no return where gravity is so strong that not even light can escape. It is a shadow cast against the backdrop of spacetime itself. The technical achievement behind this single image was itself a source of shock. A black hole that massive is paradoxically an incredibly tiny target in the sky. To see it required a telescope with a resolution sharp enough to read a newspaper in New York from a sidewalk cafe in Paris. To achieve this, astronomers did not build a bigger dish. They built a virtual telescope the size of our entire planet. The Event Horizon Telescope is a network of 8 radio observatories, from the high deserts of Chile to the peaks of Hawaii, from the frigid South Pole to the mountains of Spain. By synchronizing these dishes with atomic clocks and pointing them all at M87 for several nights, they created an interferometer, a single Earth-sized eye. The amount of raw data collected was staggering, so vast it could not be sent over the internet. The hard drives, filled with petabytes of information, had to be physically flown to central processing centers. Teams of scientists then spent years using sophisticated algorithms to piece together this celestial portrait from the fragments. The result was more than a pretty picture. It was a brutal, beautiful test of physics in the most extreme environment imaginable. The size and shape of that dark shadow matched Einstein's equations with stunning precision, even under gravity millions of times stronger than our Sun. In one iconic image, a century of theoretical prophecy was made flesh. A cosmic phantom was dragged into the light, and humanity gained a new, visceral understanding of the darkest objects in creation. The first image of a black hole's shadow was a triumph of prediction, a violent confirmation of Einstein's vision in the most extreme arena. But decades earlier, cosmologists faced a different kind of cosmic crisis, one that threatened to unravel the story of the Big Bang itself. The problem was deceptively simple, yet profoundly deep. It was called the horizon problem. When we look out into space, we are also looking back in time. The cosmic microwave background radiation, the afterglow of the Big Bang, comes to us from every direction in the sky. This ancient light reveals a universe that was remarkably, impossibly uniform. The temperature of this primordial glow is the same everywhere to within 1 part in 100,000. Here is the shocking contradiction. According to the standard Big Bang model, these regions of the sky on opposite horizons of the universe had never been in contact. They were separated by distances so vast that not even light, traveling for the entire age of the universe, could have bridged the gap between them. There was no time for heat to flow from one region to another to even out the temperature. It was as if you walked into a vast auditorium and found 1,000 cups of coffee, each poured by a different person in a different city, all at exactly the same temperature to within 1,000th of a degree. Without any communication, such perfect uniformity is a statistical miracle, a cosmic coincidence that seemed too perfect to be true. The universe appeared to have been born with its conditions preset, a mystery that left scientists deeply uneasy. In the early 1980s, a young physicist named Alan Guth proposed a solution so radical it seemed like science fiction. He called it cosmic inflation. The theory suggested that in the first incomprehensibly tiny fraction of a second after the Big Bang, the universe underwent a period of exponential, faster-than-light expansion. In this model, the entire observable universe we see today was once a quantum speck smaller than a single proton. Then, driven by a strange, repulsive energy field, this speck inflated violently. In less than a trillionth of a trillionth of a trillionth of a second, it blew up to the size of a grapefruit or even larger. This was not an expansion of matter into space, but a stretching of space-time itself. This idea solved the horizon problem with breathtaking elegance. Before inflation, that tiny quantum speck was small enough for every part of it to be in causal contact, able to exchange energy and reach a uniform temperature. Then inflation took that tiny, uniform region and stretched it to become larger than our entire observable cosmos. The perfect uniformity we see in the cosmic microwave background was simply baked in from the start, then blown up to cosmic scales. But inflation did more than solve an old puzzle. It made a series of bold, testable predictions. It said that this violent stretching would have created microscopic quantum fluctuations in the energy field and magnified them to macroscopic size, seeding all the large-scale structure of the universe, every galaxy and cluster we see today. It predicted these seeds would leave a specific, faint pattern of hot and cold spots in the cosmic microwave background, a particular signature in the polarization of that ancient light. For years, it was a beautiful but unproven idea. Then, in the early 2000s, satellites like WMAP and later Planck mapped the cosmic microwave background with exquisite precision. The data they returned sent a second, confirming shock through cosmology. The patterns in the sky matched the predictions of inflation with stunning accuracy. The specific statistical properties of the hot and cold spots, the telltale signs in the light's polarization, they were all there. The theory had passed its most rigorous test. The confirmation of cosmic inflation was a monumental paradigm shift. It rewrote the first chapter of our cosmic origin story, inserting a brief, unimaginably violent prologue that set the stage for everything that followed. It explained not only why the universe is so uniform, but also where the seeds for all structure came from. In one sweeping idea, a troubling cosmic coincidence was transformed into a necessary consequence of physics, revealing a universe born not in a simple fireball, but in a burst of hyperdimensional creativity that defies all human intuition. Cosmic inflation painted a universe born from a violent, creative burst, setting the stage for everything that followed. But even our own cosmic neighborhood, the solar system we thought we knew, held a shocking secret at its very edge. For decades, we envisioned the boundary of our sun's influence, the heliopause, as a relatively smooth transition. Here, the outward pressure of the solar wind, a stream of charged particles from the sun, finally stalls against the inward pressure of the interstellar medium, the thin gas and dust between the stars. It was a frontier, but a quiet one. Then the data started to tell a different story. NASA twin Voyager probes, after their grand tours of the planets, became our first interstellar scouts. As they crossed the heliopause, Voyager 1 in 2012 and Voyager 2 in 2018, their instruments recorded the environment. They confirmed the boundary, but they also sensed something strange, a region just outside where the density of particles was unexpectedly high. It was as if the probes had entered a cosmic buffer zone, a piled-up wall of material. The real shock, however, came from looking at the big picture from within. NASA Interstellar Boundary Explorer, or IBEX, mission was designed to map the entire boundary from Earth orbit. It doesn't look at light or charged particles directly. Instead, it detects energetic neutral atoms, particles created when charged particles from the solar wind collide with atoms from the interstellar medium and steal an electron, becoming neutral. These neutral atoms, now unaffected by magnetic fields, zip straight back inward where IBEX can catch them. By mapping their arrival directions, the spacecraft could paint a global portrait of the heliosphere's outer skin. What IBEX revealed in 2009 was utterly unexpected. The data showed not a uniform glow, but a bright, narrow ribbon of intense emission snaking across the sky. This ribbon was 2 to 3 times brighter than anything else at the boundary, and it defied all initial models. It was a stark, luminous feature that no one had predicted, a great galactic barrier emblazoned across the edge of our solar system. The shock was profound. Our heliosphere was not a simple, symmetrical bubble sailing smoothly through the galaxy. It was interacting with the local interstellar medium in a complex, structured dance, and this ribbon was the clearest signature of that interaction. The leading theory is that this ribbon forms at the region where the magnetic field of the galaxy itself presses against our heliosphere. The galactic magnetic field lines which permeate the interstellar medium are thought to be draping around our solar bubble. At a specific location where these external field lines are parallel to the view from IBEX, charged particles become trapped, bouncing back and forth. This process greatly increases the chance for them to interact and create the energetic neutral atoms that flow back to us, creating the bright ribbon we see. It is a celestial imprint, a contour line on a map of invisible magnetic forces. This discovery fundamentally changed our understanding of our place in the galaxy. We are not isolated. The solar system's protective bubble is constantly being molded and shaped by external galactic forces we are only beginning to measure. That glowing ribbon is a shockingly clear signpost, revealing that the frontier of our home is not a blank wall, but a dynamic and luminous interface, a place where the sun's domain meets the magnetic heartbeat of the Milky Way. The magnetic ribbon at our solar system's edge revealed a dynamic boundary, but far beyond that local frontier lies a cosmic emptiness so vast it defies comprehension. This is the Boots Void, a region of space so shockingly barren it has earned the nickname the Great Nothing. Stretching for nearly 330 million light-years across, this void is not just a gap between galaxy clusters, it is a staggering cosmic desert, a bubble in the universe's fabric where galaxies are almost entirely absent. If you placed our Milky Way at the center of this void, humanity would have looked up at a night sky devoid of any other major galaxies until the era of modern telescopes. The discovery of its true scale delivered a profound shock to cosmologists. When large-scale surveys first began mapping the universe in 3 dimensions, they expected to find a cosmic web, a frothy structure of dense galaxy filaments and clusters surrounding emptier pockets like the holes in a sponge. But the Boots Void was not a hole, it was a chasm. Initial observations suggested it contained only a handful of galaxies, perhaps 60, in a volume of space that, according to the standard model of structure formation, should have held thousands. This was not just a statistical fluke, it was a colossal anomaly. The existence of such a vast, underdense region poses a direct challenge to our understanding of how the universe evolved from the near-uniform soup of the Big Bang into the intricate web we see today. The process is driven by gravity, where slightly denser patches of dark matter attract more matter, growing over billions of years into the filaments and nodes of the cosmic web. For a void this enormous to form, the initial conditions of the universe would have had to include a correspondingly enormous underdensity, a smooth patch on a scale that strains the predictions of cosmic inflation. It forces scientists to ask, was this void carved out by something else? One compelling theory suggests it might be the result of multiple smaller voids merging over time, like soap bubbles coalescing into one giant cavity. Another, even more mind-bending idea is that the Boots void could be evidence of an immense collision with another universe in the multiverse, a cosmic bruise on the fabric of our reality. While that remains highly speculative, the void's very existence is a concrete, shocking puzzle. It tells us that dark matter, the invisible scaffolding of the cosmos, is not distributed in a perfectly even web, but can leave behind voids of staggering scale. Studying this great nothing is just as important as studying the brilliant clusters, because it reveals the limits of gravity's creative power and the echoes of the universe's most ancient imperfections. It stands as a monument to cosmic absence, a silent, dark reminder that even in a universe teeming with structure, emptiness can hold the most profound questions. The vast cosmic desert of the Boots void revealed a shocking absence of structure on the grandest scale. But sometimes the most profound shocks come from a single point of light, a star so small it should never have been able to build the giant world now circling it. This is the story of JJ3512b, a planet that, by every established rule, should not exist. The star at the center of this mystery is a red dwarf, a common but faint type of star known as an M-dwarf. It is tiny, with only about 12% of the mass of our Sun, a dim, cool ember in the constellation Ursa Major. In 2019, astronomers using the Carmines instrument in Spain were monitoring this faint star for the subtle wobbles caused by the gravitational tug of orbiting planets. The signal they found was not subtle at all. The star was being yanked around by something massive, a planet with at least half the mass of Jupiter. The sheer scale of this mismatch sent a shockwave through the field of planetary science. For decades, the leading theory for how gas giants like Jupiter form has been core accretion. In this model, a rocky core forms first from the dust and ice in the disk of material surrounding a young star. Once this core reaches a critical mass about 10 times that of Earth, it has enough gravity to rapidly pull in and hold onto the vast amounts of hydrogen and helium gas in the disk, ballooning into a giant planet. The problem with JJ3512b is its tiny parent star. A small star means a small protoplanetary disk with far less total material to work with. According to core accretion models, the disk around this faint red dwarf simply did not contain enough gas and dust to first build a massive core and then attract a gigantic atmosphere. It would be like trying to build a mansion with only enough lumber for a tool shed. The planet's existence is a direct, glaring contradiction to our textbooks. This impossibility forced scientists to seriously consider a different, more dramatic formation process, one that had been largely relegated to the sidelines for solar systems like our own, gravitational disk instability. This theory suggests that under the right conditions, a dense, massive protoplanetary disk can cool rapidly. As it cools, it can fragment under its own gravity, collapsing directly into a clump that becomes a gas giant planet, essentially skipping the rocky core stage entirely. It is a top-down process, like a spiral arm of a galaxy pinching off to form a star, rather than the bottom-up, piece-by-piece assembly of core accretion. The discovery of JJ3512b is a stunning piece of evidence that this violent, direct collapse method might be far more common around small stars than anyone thought. This one planet forces a major rewrite of the rules. It tells us that planet formation is not a one-size-fits-all process dictated solely by the star's mass. The universe has more than one recipe for building a giant world, and around the most common stars in the galaxy, the recipe might be one of sudden gravitational chaos. Our solar system, with its orderly giants formed by core accretion, may be the exception rather than the rule, a quiet suburb in a galaxy filled with planetary systems born from far more violent beginnings. The planet JJ3512b broke the rules of how worlds are born, a testament to cosmic chaos. Yet another shock awaited in the most ancient light we can see, a relic so perfect it became the bedrock of modern cosmology, only to reveal cracks in its foundation. This is the cosmic microwave background, the CMB. It is the faint, cold glow that fills the entire sky, the cooled and stretched afterglow of the Big Bang itself, released when the universe was a mere 380,000 years old. For decades, it was hailed as the ultimate proof of a hot, dense beginning and the gold standard for a universe that is isotropic, meaning it looks the same in every direction on the largest scales. Satellites like WMAP and later Planck mapped this ancient light with breathtaking precision, confirming the predictions of cosmic inflation and measuring the universe's composition to decimal places. The CMB appeared almost perfectly uniform, a masterpiece of cosmic simplicity. But within that exquisite data, scientists found something deeply unsettling, anomalies that should not be there. The most shocking of these is a feature so strange it was given a dramatic nickname, the axis of evil. It is not an axis of malice, but a statistical oddity that points toward a profound mystery. When scientists analyze the largest scale patterns in the CMB, the hot and cold spots that span billions of light years, they expect these patterns to be randomly oriented. There should be no preferred direction, no cosmic north or south, in keeping with the cosmological principle that the universe has no special place. Yet the data from both WMAP and Planck revealed a curious alignment. Certain large-scale fluctuations, the ones that represent the most fundamental ripples in the infant cosmos, seem to line up along a particular axis in space. It is as if the universe has a subtle, ghostly fingerprint, a faint directional preference imprinted at the moment of its birth. The implications of this are staggering. If the axis of evil is real and not some colossal statistical fluke, it challenges the very foundation of modern cosmology. It suggests that the universe might not be isotropic after all. There could be a preferred direction on the largest scales, a cosmic grain like the texture of wood, contradicting a principle we have held as sacred for a century. What could cause such a thing? Theories range from the mind-bending to the revolutionary. Perhaps our entire observable universe is just one bubble in a vast multiverse, and we are seeing the gravitational tug or imprint of a neighboring cosmos, a bruise from a collision with another reality in the primordial past. Or maybe it is a sign that cosmic inflation, while brilliantly successful, is not the full story, and some other, more complex process set the initial conditions. Some have even suggested it could be evidence of a universe that existed before our Big Bang, a cyclic cosmos where each new expansion inherits a faint memory from the previous contraction. The axis of evil remains an unsolved, haunting puzzle. It is a whisper from the oldest light telling us that for all we have learned, the cosmos might still hold a fundamental surprise about its own shape and origin. The shock is not that the standard model is wrong, but that it might be incomplete, that the universe's first light carries a shadow of direction we do not yet understand. The axis of evil whispers of a cosmic direction we cannot explain, a ghost in the machine of the Big Bang itself. But what if that whisper was not just a pattern but a pull? This brings us to one of the most controversial and mind-bending shocks in modern cosmology, a phenomenon known as the dark flow. Imagine you are standing in a vast, calm sea. All around you, the water is still, but you notice over time that every single piece of driftwood, every leaf, every floating object is drifting slowly but surely in the same direction. This is not a local current, it is a vast, coherent motion that suggests something immense is pulling on the entire sea from beyond the horizon. That is precisely what astronomers think they may have detected in the motions of entire galaxy clusters. The discovery came from studying the cosmic microwave background in a unique way, using something called the kinetic Sunyaev-Zeldovich effect. When the hot gas in a massive galaxy cluster moves through space, the photons of the CMB radiation, the ancient light of the Big Bang, scatter off the electrons in that gas. This scattering leaves a tiny, specific imprint in the CMB's temperature, a fingerprint that reveals not only the cluster's presence, but its velocity through space. A team led by astronomer Alexander Kashlinsky analyzed data from hundreds of these massive clusters, looking for any common direction in their motion. What they found was staggering. The clusters were not moving randomly. They appeared to be streaming together at incredible speeds, over 600 miles per second, toward a single patch of sky between the constellations Centaurus and Vela. This motion was on a scale of billions of light years, a coherent flow of the largest structures in the universe. The shock was absolute because, according to our standard model of cosmology, there should be no such flow on this scale. The gravitational pull from all the matter in the observable universe should cancel out, leaving no preferred direction for such a vast exodus. The only plausible explanation was even more shocking. The dark flow suggests that these galaxy clusters are feeling the gravitational tug of something truly unimaginable, a structure of staggering mass that lies far beyond the edge of our observable universe, beyond the cosmic horizon from which light has had time to reach us since the Big Bang. What could possibly be that massive? One terrifying and thrilling possibility is that we are seeing the gravitational influence of another universe, a neighboring bubble in a vast multiverse, exerting a pull on our own cosmic domain. It is a hypothesis that sounds like pure science fiction, yet it emerged from meticulous analysis of real data. The controversy is fierce. Other scientists have questioned the statistical significance of the finding or proposed alternative explanations involving subtle instrumental effects. Yet, if the dark flow is real, its implications are beyond profound. It would be the first empirical hint that our universe is not alone, that our Big Bang was just one event in a far vaster, richer multiversal landscape. We would have to accept that the greatest structures influencing our fate lie not just in the darkness we can see, but in the infinite darkness we cannot. It is the ultimate cosmic shock, the possibility that we are not the center of everything, but merely a leaf floating on a sea being pulled by a tide from another shore entirely. The possibility of a pull from beyond the visible cosmos challenges everything we think we know. Yet for decades, cosmologists faced a different, more concrete crisis, a cosmic inventory that simply did not add up. We call this the case of the universe's missing matter. Not dark matter or dark energy, but the ordinary stuff you and I are made of, the protons and neutrons known as baryonic matter. The Big Bang's recipe is exquisitely precise. By measuring the cosmic microwave background, scientists can calculate exactly how much of this ordinary matter should exist in the universe today. But when they added up everything they could see, all the stars, galaxies, and glowing gas clouds, they came up shockingly short. Nearly half of all the normal matter in the cosmos was simply gone, vanished without a trace. For years, this missing half represented a profound embarrassment, a hole in our understanding of cosmic bookkeeping. Where could it be hiding? The leading suspicion pointed to the vast, empty spaces between galaxies. Not the boots void, but the very filaments of the cosmic web itself, the scaffolding along which galaxies are strung. Theorists propose that this missing matter must be hiding there in the form of an incredibly diffuse, superheated gas, a medium so tenuous and hot it emits almost no light we can detect. They named it the warm-hot intergalactic medium, or the WIM. The name sounds gentle, but this is a plasma seething at temperatures between 100,000 and 10 million degrees, a ghostly web stretching across billions of light years. Finding it was the challenge of a generation. You cannot photograph emptiness. You need a flashlight, a backlight bright enough to shine through this invisible fog and reveal its shadow. Astronomers found their perfect tool in the most violent events in the universe, quasars. These are the blazing cores of distant galaxies, powered by supermassive black holes feasting on matter. By training telescopes on quasars and analyzing their light as it traveled through the cosmos to reach us, scientists hunted for telltale absorption lines, specific wavelengths of light that would be subtly absorbed by the oxygen and other elements thought to be floating in the WIM. For years, the evidence was spotty, hints and whispers. The shock came when they turned to a newer, more powerful cosmic flashlight, fast radio bursts. Remember those millisecond screams of radio energy from distant galaxies? Their journey to Earth is a marathon through the cosmic web. As a fast radio burst passes through the WIM, its different radio frequencies are slowed down by the ionized gas, just like light bending through a prism. The degree of this dispersion, how much the burst is stretched out, directly reveals the total amount of ordinary matter it has traveled through. When astronomers began analyzing the dispersion of bursts from known distances, the numbers finally matched. The missing matter had been found. It was not in glorious galaxies, but in the faint, hot breath between them, a gauzy web of gas so diffuse that a cubic meter of it might contain only a few atoms, yet spanning such immensity that it accounts for half of all normal stuff in existence. This discovery closed one of cosmology's most stubborn cases, transforming a shocking absence into a confirmed, if ghostly, presence. It completed our census of the ordinary universe, proving that what we see shining in the night sky is merely the glittering ornamentation on a vast, dark, and surprisingly warm foundation. That census of the ordinary universe, the warm gas between galaxies, is the quiet backdrop for a stage where the most extreme objects can perform acts of pure cosmic violence. In March of 2023, the Hubble Space Telescope captured one such performance so bizarre it seemed to defy the laws of celestial motion. It spotted a supermassive black hole, an object synonymous with gravitational imprisonment, doing the one thing it should not be able to do. It was running away. Streaking across the emptiness between galaxies was a black hole with the mass of 20 million suns, and it was not sitting quietly at the center of a galaxy. It was free, a cosmic cannonball blasting through intergalactic space. The sheer spectacle was shocking enough, but Hubble's keen eye revealed an even more beautiful and impossible detail. In the black hole's wake, stretching back to a now distant galaxy, was a narrow, brilliant corridor of young, blue stars. It was not a trail of destruction, but a river of creation. This titanic fugitive was not consuming everything in its path. Instead, its unimaginable velocity, calculated to be over 5 million miles per hour, was triggering star birth. The leading theory paints a scene of gravitational drama worthy of a cosmic opera. Imagine 3 supermassive black holes, each the ruler of its own galaxy, brought together by a galactic merger. In the chaotic dance that follows, 2 of the black holes can spiral in and eventually merge, releasing a tsunami of gravitational waves. Like a rocket firing in one direction, this burst of energy can kick the newly merged black hole backward. If a third black hole is present in just the right position, it can act as a gravitational slingshot, catching this recoiling monster and hurling it entirely out of its host galaxy. This is not science fiction, it is a direct prediction of Einstein's theory, a phenomenon called gravitational wave recoil. What Hubble may have witnessed is the first real evidence of this process in action. A supermassive black hole ejected by the pure force of ripples in spacetime itself. The trail of stars is the beautiful accident left behind. As the black hole plows through the thin gas that permeates intergalactic space, its tremendous speed compresses the gas ahead of it like a cosmic plow. This compression triggers the collapse of gas clouds, lighting the fuse for new stars to ignite in a straight line behind the speeding behemoth. The shock here is multifaceted. It is the shock of seeing an object we think of as an immovable anchor become a projectile. It is the shock of witnessing destruction give birth to creation. And it is the profound shock of catching, in a single image, a live demonstration of the most powerful forces in the universe conspiring to rewrite the rules of where a black hole belongs. This runaway giant is a smoking gun for the violent, chaotic mergers that shape galaxies, and a stunning reminder that even the darkest hearts of galaxies can be sent flying, leaving a streak of light across the void. A runaway black hole paints a picture of chaos, a celestial giant flung from its home. But another black hole, much closer to home, has been caught performing a very different kind of act, one of eerie metronomic precision. It is called GRS 1915+105, a mouthful of a name for one of the most bizarre objects in our galaxy. This is a microquasar, a stellar black hole about 14 times the mass of our Sun, locked in a deadly dance with a normal star. It feeds on its companion, pulling gas from it into a swirling, superheated disk of doomed matter. For years, telescopes watched its X-ray output, expecting the usual chaotic flicker of a messy cosmic dinner. What they recorded instead was a profound shock, a rhythm. Every 40 minutes, like clockwork, the X-ray emission from this system would spike, then plummet, then spike again. This was not random noise. It was a near-perfect heartbeat, a pulse emanating from the very edge of oblivion. The stability of this signal was as shocking as its existence. This heartbeat has been repeating, unwavering for decades, a cosmic metronome ticking through the darkness. This rhythmic signal is a gift, an unprecedented real-time probe into the most violent physics imaginable. Astronomers realized they were not just watching a black hole eat, they were watching it choke. The leading model is a breathtaking cycle of feast and famine right at the precipice. Imagine the accretion disk, that swirling river of hot gas, as having two states. First, a quiet state where material builds up in the inner part of the disk like water behind a dam. This is the low point of the heartbeat. Then the dam breaks. The piled-up gas suddenly rushes inward toward the black hole, heating to millions of degrees and unleashing a tremendous flash of X-rays, the spike in the pulse. But this influx is too much, too fast. The black hole cannot swallow it all at once. The excess material gets funneled into powerful, narrow jets that blast outward at nearly the speed of light, clearing out the inner disk. With the inner region emptied, the system resets and the quiet building phase begins again. The 40-minute period is the time it takes for this entire cycle to complete, a direct measurement of how long it takes for that inner dam to fill and burst. This heartbeat lets scientists watch in real time the intimate connection between the accretion disk and the relativistic jets, a feedback loop of matter and energy playing out just outside the event horizon. It is a laboratory for Einstein's physics, a window into how black holes regulate their own diets and shape their surroundings with rhythmic bursts of power. In the chaotic violence of a black hole's grasp, we found a steady pulse, a shocking testament to the hidden order within the storm. The steady heartbeat of a black hole revealed hidden order in the chaos, a rhythm we could measure and understand. But the greatest shock of our era comes not from a single object, but from a flood of data so revolutionary it threatens to break the cosmic timeline itself. This is the legacy of the James Webb Space Telescope. After its spectacular launch and deployment, the world's most powerful observatory turned its golden eye toward the deepest reaches of space and time, aiming to capture the very first galaxies being born in the cosmic dawn. Scientists expected to see faint, infant smudges, small and chaotic collections of stars just beginning to coalesce from the primordial soup. What Webb saw instead left the global astronomical community in a state of stunned disbelief. It found galaxies, but they were not infants. They were cosmic titans, massive, mature, and fully formed, existing at a time when the universe was only a few 100 million years old, a mere 2 to 3% of its current age. According to every established model of cosmic evolution, this was simply impossible. There had not been enough time since the Big Bang for gravity to gather that much ordinary matter, to build stars, for those stars to live, die, and enrich space with heavy elements, and then to assemble into such colossal, structured galaxies. It would be like finding a thriving, modern metropolis in the middle of the Stone Age. These galaxies, nicknamed universe breakers, are not just a little off the models. They are off by orders of magnitude. Some appear to be as massive as our own Milky Way, a galaxy that took over 13 billion years to build, yet they are seen when the universe was 30 times younger. The immediate shock forced a frantic re-examination of every assumption. The first and most hopeful line of inquiry asked if the measurements themselves were wrong. Perhaps the light from these galaxies was not as ancient as it seemed. Could interstellar dust be reddening the light of closer, younger galaxies, tricking Webb's instruments into thinking they were more distant and ancient? Meticulous follow-up observations have largely ruled this out. The spectral fingerprints, the definitive proof of distance and age, confirm these galaxies are indeed where they appear to be, shining from the edge of time. With measurement errors fading, the shock deepens into a profound theoretical crisis. If the data is correct, then our fundamental story of how structure forms in the universe is incomplete, or worse, fundamentally wrong. One possibility is that the early universe was far more efficient at making stars than we ever dreamed, perhaps due to exotic, never-before-seen populations of super-bright stars. Another, more radical idea is that we are seeing the fingerprints of a different kind of physics in the early cosmos, perhaps involving dark matter that is not cold and sluggish, but warm and fast-moving, allowing it to clump together and seed galaxies much faster than our models allow. The most extreme conclusion is that we need to completely redraw the timeline of cosmic dawn, moving the beginning of galaxy formation startlingly closer to the moment of the Big Bang itself. This is not a quiet adjustment, it is a potential revolution. The James Webb Space Telescope, built to answer our oldest questions about the universe's infancy, has instead handed us our greatest modern puzzle. These universe breakers are not just distant objects, they are cracks in the foundation of cosmology. They represent the thrilling, terrifying moment when observation overtakes theory, when the cosmos looks back at us and reveals a history we never dared to write. The debate now raging in observatories and journals around the world is the sound of science at its best, shocked into a new reality and forced to imagine a universe far stranger and far more creative than we ever believed possible. These universe breakers are more than just cosmic anomalies, they are profound teachers. Each of the 25 shocks we have explored, from the silent ghost of the WOW signal to the impossible galaxies seen by the James Webb Telescope, shares a common, vital thread. They are not random accidents in the data, but moments of profound instruction from the cosmos itself. True scientific discovery rarely arrives as a gentle confirmation of what we already believe. More often, it crashes into the laboratory as a contradiction, a piece of data that simply will not fit into the neat puzzle of our existing theories. This is the essential, uncomfortable, and beautiful engine of progress. Being shocked is not a sign that science has failed. It is the definitive proof that science is working exactly as it should. The universe is pushing back against our assumptions, guiding us, sometimes forcefully, toward a deeper and more accurate truth. Think of each of these moments not as isolated scandals, but as vital clues in the greatest detective story of all time. The Pioneer anomaly was a whisper about the importance of engineering humility. The accelerating expansion of the universe was a scream that we had missed 68% of reality. The Martian methane plumes are a persistent tap on the shoulder, reminding us that a world we declared dead might still be breathing. Every shock is a puzzle piece, and while we have connected many of them into a coherent picture of cosmic evolution, the edges of that picture are still ragged and incomplete. The framework is there, but vast sections remain empty, waiting for the next shocking discovery to click into place and reveal a shape we cannot yet foresee. This is the thrilling, endless nature of the quest. We build the best models we can with the pieces we have, and then we send out new telescopes, new probes, new minds to gather more. We are not just cataloging wonders, we are being schooled by them. Each gasp of disbelief in a control room, each frantic recalculation on a chalkboard, is the sound of human understanding being stretched, broken, and reformed into something stronger and stranger. The cosmos is not a static museum to be understood, but a dynamic teacher that constantly challenges its students. Our greatest tool is not infallibility, but our capacity to be surprised, to admit when we are wrong, and to follow the evidence into the dark, no matter how shocking the path may be. So the journey ends not with a final answer, but with a deeper sense of wonder. From a single, silent radio signal to galaxies that break the cosmic timeline, we have traveled through 25 moments that left the world's top scientists utterly speechless. Each shock, whether a geometric storm on Saturn or a planet that defies its own star, has been a lesson written in starlight and shadow. They reveal a universe that is not a placid, predictable clockwork, but a dynamic, creative, and often violent arena where the rules are constantly being tested and rewritten. The fundamental takeaway is both humbling and exhilarating. The cosmos is far stranger, more complex, and more wonderful than our boldest science fiction dared to imagine. This is the beautiful, endless work of discovery. It is a process built not on certainty, but on our capacity to be surprised, to have our most cherished models shattered by a new piece of data, and to find the courage to build a better, stranger understanding from the pieces. The human story is one of looking up at the night sky and asking questions. Every shock on this list is proof that the universe is listening, and it is answering in ways that constantly redefine the possible. So keep looking up, stay relentlessly curious, embrace the unknown not as a void, but as a frontier filled with whispers waiting to become revelations. Remember, the next great cosmic shock, the one that will once again rewrite the textbooks and leave us all in awe, could be just one telescope observation away. It is out there, hidden in the data, waiting for the right mind to notice. Which of these 25 moments amazed you the most? Let us know in the comments below, and subscribe to join us as we continue our deep dives into the greatest mysteries of space. The universe is not done surprising us yet.